Okay, good afternoon. I hope you can all hear me. Yeah, I think today is my pleasure to introduce Professor Peter Tiňo, a very interesting talk, learning from temporal data using state space models. I think you probably have seen the abstract. I'll probably just give a quick introduction to Peter. The talk, I think Peter already gave to a conference held in Manchester 2 years ago, well, just less than 2 years ago, 2019 at the RDU conference. I thought it was excellent talk, was well received. I thought that would benefit this community, so that's why I invited Peter to talk this again. I think this is really, really good coverage in terms of theoretical aspect. In terms of temporal modeling, I think most of you probably have come across LSTM, or if you're back a bit early, regression models, and then also probably early, the echo state models. And then people just take for granted, use these models for their modeling, for their temporal or sequence analysis tasks, without really looking into why or how it works. I think certainly the entire deep learning is going that way, isn't it? So from very traditional orthogonal representation to over complete representation, and then mirror that to the convolutional neural network, as long as you have a set of kind of features, and you can then distinguish, use those to kind of different objects. So in temporal modeling is quite similar. The reservoir kind of approach to have kind of a reservoir of many, many possible simple dynamic models. So then you can use to model any kind of a complex phenomenon. So that kind of things I thought would be useful, and I thought Peter's talk was excellent to cover this the kind of uniform foundation of that. So Peter is a professor of complex and adaptive systems at the School of Computer Science at Birmingham. Has authored over 160 research articles in the areas of dynamic systems, machine learning, and natural computation, and fractal geometry. Peter has been awarded 3 outstanding Journal of the Paper of the Year awards, usually by top journals, and also the head of school's Excellent in Teaching Award. Professor Tiňo is also a co-supervisor of ECHO, the Innovative Training Network for Early Stage Researchers, funded by EU Horizon 2020 Research and Innovation Program, and the grant agreement number 766186 is based on a novel synergies between natural inspired optimization and machine learning. To me, machine learning and optimization is always two sides of a coin. The training programs also be targeted at the automotive industry, and early stage research employed on the program will be provided with transferable skills necessary for driving careers in emerging and rapidly developing industrial areas. So over to you, Peter, so yours.
Okay, thank you, Hujun, for a kind introduction. So guys, I'm going to share the screen now. This one, probably. Right, you tell me if you see the slides now. Everything is okay? Hujun?
Yeah, that was good.
Okay, perfect. Okay, great. Okay, thank you all for coming. I can recognize Danny Wood. Hi, Danny. He has an excellent PhD thesis. Anyway. Hi. Hi. So, right. Today's talks is going to be a little bit unusual. And it will be unusual in the sense that it's not going to be presentation of the most recent research findings on a very specific particular area. I gave a tutorial on state space modeling in general, the ideal, and as Hujun mentioned, and I actually realized that because lots of people are nowadays using LSTM and other gating type of recurrent neural networks because they are part of a package that is freely available, I found that sometimes the users don't really understand what is going on and don't understand really the issues. So then I thought about preparing a presentation that will build things up from the basics and bring up issues that are common to all state space models, in particular LSTM and other models, and recurrent networks are just particular cases of state space models, but it's good to have this broad view. And so that's the purpose of this talk. Of course, I will not be able to cover everything, because what we are really talking today about is recurrent neural networks, hidden Markov models, autoregressive models, ARMA, ARIMA, all these models are state space models. And I claim that they have the same foundational basis, and some of the issues are the same for all these models, right? So let's just go. So these are just a few of the people who contributed to the work. And I would just like to express my thanks to them. Those are my collaborators, not all of them, that helped me to develop these things over the years.
Peter, I can only see the first slides.
All right, so you don't see the slide dynamical processes?
No.
Okay, let me deal with it. All right. Okay.
Yeah, now, yeah.
Right, I can write. And now, can you see it now?
Yeah, I can see slide 3 now.
Right, perfect. Okay, great. Okay, thank you, Hujun. Right, so here we start. So we have a problem where the data comes in time. We call it time series, and usually what happens is that there is some underlying dynamical process that is generating my observations. And usually the dynamical process can be characterized by what we call a state of the system. So it's everything that is important in order for that system to evolve in time. And we usually denote it by xt, and it comes from a calligraphic x, which is like a state space. It can be, of course, a finite dimensional interval. It can be infinite dimensional. It can be whatever. It can be even discrete set. And what happens is that this underlying dynamical process is evolving in time. Now, we can track the process of the system in discrete time steps. And in that case, we talk about discrete time. And those are the systems that you can see here, the equations. And the dynamics can be autonomous. That means if I want to know the state of the system at time t, all I need to know is the state of the system at time t minus 1. And there is the dynamical law here represented by F that tells me what is the so-called state transition function that takes me from the previous state to the new state. Of course, things can be non-autonomous. That means you can be either excited by an external input that is denoted by ut here, or this can be an external noise or something else. However, what I wanted to stress here is that the next state at time t not only depends on your previous time step, but also on some other underlying factors, which can be your external inputs, for example. Now, the dynamics can be continuous time, not discrete time. And in that case, we will be dealing with ordinary differential equations, as you can see at the bottom of the slide, where we can see that the state evolves continuously in time as described by the differential equation. And of course, this can be in an autonomous regime where the only thing that matters is the state, or you can again have external inputs, external driving source, external noise, whatever. So this is non-autonomous dynamics. So those are all instantiation of how do we capture the dynamical process that is generating our observations. Now, let's go further down. The dynamical processes can be either stationary or non-stationary. So what I mean by stationary is everything that I was talking about in the last slide. What I mean by non-stationary is described here. Note that there is a little time index in F in the mapping, and that means that actually your mapping now depends also on the time. So you can imagine that you have a time series, for example, in finance, where you can have high volatility periods or relatively calm periods, and the law that describes how your system is changing is not the same anymore. It really depends on your particular time. And of course, then you can have either discrete time regime or continuous time regime, which is in here. So this is non-autonomous, non-stationary dynamics. Now, the final thing I would like to say is that you can either have deterministic evolution, and that again is everything that I was describing so far, or probabilistic or stochastic. Now, in this case, if you look at the equations below, we have conditional probabilities, and that means...
Peter, the slides are not...
Peter, slides are not moving.
Sorry?
It's still slide 3.
Really? Okay.
Yeah. So I'm not sure if you can.
I will stop sharing. I will stop sharing, and I will just do it again. Okay. I don't understand what is going on, but what I will do is I will just share the whole screen.
I always had a problem with the sharing screen. Zoom.
Yeah.
One thing you could do is to do the full screen mode, Peter.
Yeah.
Okay, that's better. I think that should do that.
You should see a slide dynamical processes.
Yeah, that's.
Do you see
correct.
right? Do you see slide?
That's perfect now. Yeah, it's perfect now.
So what I was describing here is dynamical processes. So this is where your current state xt depends on the previous state xt minus 1, or it can depend on the previous state and current input. So you can be excited. This is discrete time. Then you can have differential equations if you have continuous time. And you can your mapping can be fixed, in which case your regime is stationary. So that means the dynamical law is not changing, or it can be non-stationary, where there is a time index t, meaning that this dynamical law itself can change in time. And again, you can have discrete time and continuous time. Now, it can be deterministic, and that's everything that I was describing so far, or it can be probabilistic or stochastic, and that's here. So what do I mean? If you tell me exactly what your state is, so if I condition my probability distribution, conditional on my previous state, xt minus 1, there's still only a distribution over the next state, right? So instead of a deterministic, you now have distribution over possible states. And this can be in the deterministic regime, as you can see here, or in the autonomous regime or non-autonomous regime that is here. So we only have probability distribution over the next states, right? Now, all that I was describing so far are ways we capture the underlying development of the underlying dynamical system that is generating the observations. So the tool that we have at our hand is a state of the system. And here is how I capture the development of the state, right? Now, the thing is, I need to observe the system. So how do I observe the system? Well, we call it either readout function or observation function. And that's a function h that you can see here. And given the state of the system, you read out the system in terms of observations. So it's like your telescope on the system that is in there, right? And it can have both forms. It can have this form that it depends on the state and your current input, or everything is captured in the state. In other words, from the underlying system, you only can observe certain aspects. And what aspects from the underlying system you observe depends on this mapping H that takes some kind of information from the underlying system. Again, this is deterministic. It can be also probabilistic, meaning if I give you a precise information of the state of the system, which many times I don't have, but anyway, if I had, I can only give you a probability over a distribution over your outputs, meaning many things can happen. They can happen with different probabilities, but many things can happen. So I have a conditional distribution over my outputs given the state. And again, you can have this driven systems form, right? So this is a very, very general view of state space systems. And what they all have in common is that there is an underlying system, and I can capture what it is doing through the notion of the state that evolves, and that's these equations. And then I can observe the system through an observation function or through a probability distribution that actually encompasses this observation function, but it's only in terms of probability densities. Now, if you know about recurrent neural networks are a particular type of these state space models. Markov models are another type of state space models. Hidden Markov models are another type of the state space model. Kalman filters are another type of state space models. It's exactly everything can be written in terms of these equations, to the higher level equations. ARMA models, autoregressive models, they are all state space models. So it's a huge class of models. And other types of models that I will talk about next. But here is a little recapitulation. First, we have an underlying state of the system, and there are different ways in which you can capture how you get from the previous state into the next state, how your system evolves. Here are different things that I was talking about: discrete time, autonomous, non-autonomous, continuous time, autonomous, non-autonomous, stochastic dynamics, right? And so on. Of course, you can have also stochastic dynamics in continuous time, and then we talk about random processes, but that's much more difficult to handle, right? Okay, and then we talked about the readout functions. How do I get from my state to my observations? Now, an important notion is the notion of observable states and non-observable states. We will get to it. In general, observable states are states that you can guess very easily from your observations. So your observations give you enough information to know in what state your system is. In many cases, we don't have this luxury, and then we have unobservable states, and not surprisingly, this messes up things a lot. Right, so now I have only observations, and we are basically in this situation where I need to guess what is my underlying state system doing that I'm trying to observe and I'm trying to model, because maybe I will try to do some predictions. Now, under some condition, you can turn the observations into an information about the state. And you will see a very simple example very soon. But I also, for those of you who know about a little bit about dynamical systems, there is something that is called Taken's theorem. And the theorem says that under some relatively mild conditions, you can basically create a leg of your past observations. So you have an observational window and you slide the window through the observations. And if the window is large enough, if you observe lots of observations, you will get a pretty good idea about the underlying attractor of the system. So the structure around which the dynamics evolves in the state space. But of course, it's up to topological conjugacy. That means, you know, if your underlying attractor is a circle, with this technique, you may recover a square or a triangle. But, you know, for topology, square is the same thing as circle. So, right, so up to a topological deformations, one-to-one and continuous in both forward and backward. Right, but this is a quite specific situation. And let me just talk about the issues that one may have with trying to learn these state space systems from the observations. Well, first of all, this is a talk that is related to machine learning and AI and data science. So a large portion of state space models are constructed by hand by scientists, because they have pretty good idea what the underlying system is like. So, for example, if you do a weather system, those things are pretty hard coded in terms of equations, and there is very little to learn actually. What is difficult is to make inferences, because the systems are very complex and very large. But what I would like to talk about now is that what is of more interest to us as, you know, people who are doing something around machine learning. And that's, you know, how can I get a state space model that is pretty good at modeling my underlying system if I only have the observations? That's all I have. And I thought that we need to start very simple. And what can be simpler as to say that I have only a finite number of possible inputs that I can see in my time series. So I will only have an alphabet of symbols, and I will observe time series of symbols, but time series of symbols we used to call strings. So strings over the alphabet, and we just go left to right. We walk through this through the string. But the things that I'm going to mention here are general enough. It's easier to understand in this setting, but they are general enough to also hold for other settings. So this is the environment, whatever it is, and it is generating these long sequences for us. And now we need to make some sense of this. But the crucial thing is that what people forget about is that the first question should be, what do you want to do, right? Do you want to model the system, or do you want to make a prediction? Do you want to classify the sequences, the time series that come out? For example, you have like ECG signal and you want to classify whether something is wrong, and maybe you want to localize what that thing is that went wrong. Or you want to classify EEG signal into sleep stages. You want to find a gene in a long series of genomic sequence. So those are all classification tasks. Or you want to do modeling, or you want to do prediction because you work in a stock market and you would like to know whether the volatility of the market is going to be up because you want to trade straddles on options and so on. Now, believe it or not, modeling is not the same as prediction. Those are different criteria. For example, if I have a chaotic system, I may wish to relax my strictness about short-term prediction accuracy and trade it off for a long-term modeling accuracy in terms of how good my model of the strange attractor is. Because I care less about following in the short time scale the trajectories, and I care more about covering all aspects of the strange attractor with my model. So those are all quite important things that need to be taken into an account. And let's just think about what normally people do, and you will see an example very soon. Now, I observe these sequences. They can be of different lengths that can be even left infinite sequences mathematically. And I observe those things, and I would like to do some tasks. So let's just think about, for example, prediction or classification, right? Now, the normal thing that people would immediately do is to say, even though I observed lots of different past histories, if different past histories lead to the same continuation. So I may have observed different evolutions of the stock market, but given those, say, through 2 or 3 histories of stock market, I know that the future evolution of the market is almost the same. Then I can collapse those things into one bag. I just put them in one bag and say, to me, they are the same. Why? Because with respect to my task, they are indistinguishable. I can forget about the particular details of what they have because they lead to the same future evolution. And we call this trick a trick of representing my past histories of what I have seen and collapsing all past histories into so-called information processing states. Mathematically, these are equivalence classes over your histories of sequences that you have seen before, because you can collapse things if they lead to the same, for example, future continuation, if your criterion is prediction, or they can lead to the same classification if your criterion is classification, and so on. The important thing is to remember that information processing states code everything that is important in the past for what we want to do in the future. Right. Here is an example. So everybody who studied computer science will immediately understand what this is, right? So this is a so-called finite state automaton, and it is basically doing classification of time series. And the time series can be of different lengths, but what it is doing is this. You observe time series over 2 symbols, A and B, and I will tell you, it doesn't matter how long your sequence is. Simply, if the number of B's is odd, then you say that this is a grammatical, this is class +1. If the number of B's in your sequence is even, then it's class -1, and it's not grammatical, right? And now you see lots of symbols, they come as a time series. Now, what you do in computer science is you construct a model like this, and what this means, we have two states. They even call it states, right? So it's the same thing. So this is a state space model, right? They call it states, and you have two states here, only 1 and 2, discrete number of states, finite. And on symbol, I start here where the arrow is, and when I see symbol A, I stay. I may stay here for 1 billion times, it doesn't matter. As soon as I see B, I hop into state number 2. And again, if I see A, I stay here, because that's not relevant. A's are not relevant. And when I see B here, I go here. Immediately very clear what this model is doing and why it is a good model, right? So what is nice about this is that we immediately see that there is a state transition function, and the state transition function tells you that if you're in state 1 and you have input A, then you stay in state 1. If you're in state 1 and your input is B, you go to state 2 and so on. And you immediately see the readout function, because if you're in state 1, the output is -1. And if you are state 2, the output is +1. So it's a classical state space model, right? For the time series. And note that B1 is basically an equivalence class over all possible time series over symbols A, B that you can imagine that have simply an even number of B's, including 0, and 2 is a huge bag, huge equivalence class of all time series that contain even odd number of B's, right? So here is the simplest state space model that you have. I think somebody wants to come to the waiting room. Anyway, so so somebody's in the waiting room, right? Now let's think about, right, so what is interesting about this is that I knew what is the task, and I knew immediately, because the task was simple, how to construct the state space model. So there is no learning here, right? I just constructed it. But if you, for example, you face a problem of predicting the future, and I tell you, well, I don't know what your state space model is, then how would you go about it? So here's the thing that people do. They say, well, if we don't have any clue about what the possible state space can be for this problem, let's just say that what happens in the future, it depends only on the history of very few last entries in my time series. For example, if you do stock market prediction, and you have a daily data, you may decide to base your prediction based on the past week, which is 5 working days, right? So this is this idea. So we call this a Markov model. So this Markov model is a 5th order Markov model, because I concentrate on the 5 most recent entries, and I claim that I can forget about everything that came before, right? So that's why all these sequences that you see here, and many, many others that have the same property, that they finish with the same suffix, they all are in the same equivalence class. Simply, this is an information processing state that I can call 43211, right, based on the suffix. So you can see it's a big equivalence class of all possible sequences that finish like this. The problem with this is that this is a very good idea, but first you need to know how long your memory should be. Why it should be 5th order? Why not 10th? Why not 1st? And that's the first question. And the second question is, who is going to estimate all these probabilities? Because these are all conditional probabilities you need to estimate, right? Because you need to build probability densities over the future symbol, which are listed here, given all possible contexts of length 5 you can observe. Well, there's lots of them, as we know. It's 4 to the power of 5, which is like almost 1,000. That means that you need really very long sequence in order to statistically properly estimate all these probabilities. That's not very good, right? So it's computationally very demanding if you have long memory, and very long sequences are needed to obtain, because the number of information processing states grows exponentially fast. And they are so-called finite memory models because you only assume that only a certain portion of your recent history is important for your predictions, right? So people actually came up with a very neat idea to use a deep memory when it's really needed. So I can go deeper in the past, but not always, because it's very wasteful, right? Why should I always go 5 symbols? Maybe sometimes I need only 1 symbol, maybe sometimes I need 10 symbols. And this is the idea of prediction suffix trees. These are models that have been developed in information theory for a very long time. So if you read IEEE transactions on information theory, you will, especially in the past, you will find lots of papers on universal information sources. And prediction suffix trees are particular cases of that. But you use deep memory only when it's really needed. So here is an example. So actually, I give you a nice example from the natural language. If your past 3 symbols that you see is I and G, I think it's pretty clear that the next symbol that comes is a space, because it's probably a verb, like doing or working or something. So if you see other combinations of symbols, you may be less certain about what are the possible continuations, and then you need to look more deep into the past. Right, so how to represent it? Imagine that this is your time arrow, and this is where you are at time t, and in this way, so when you go from right to left, you go back into the history. And depending on what you have seen, you may end up in the final node, or you may decide to go deeper. So for example, if you saw 1, you can already make a prediction, but if you saw another one, you can make a better prediction, but then you don't need to go any deeper. If you saw 2, you ask, well, wait a minute, what was before? Was it 1 or was it 2? If it was 1, it's enough. You can make a prediction. If it was 2, you need additional information. You need to go further in the past, right? So this is the idea of variable memory length Markov model. So it's a Markov model, but you have flexible memory. And as you can see, it has a very nice representation in terms of a tree. And we call those things prediction suffix trees. And you will see very soon why I'm talking about these things. Now, of course, everything that I was talking about so far was when we had a discrete number of states, right? Because in this case, we had 1,000 states, but it's still a discrete set of states. In this case, when we have variable memory length Markov model, it's a discrete finite number of states. But you can imagine that this, for example, can be an n-dimensional interval, and you can indeed have a mapping that takes you from a previous state, which can be simply a member of R to the D or whatever. So it can be a real valued vector. Given current input, it can give you the next state. Now, at the moment, just for a moment, we can stay in the realm of discrete set of inputs. Okay, so this dynamical system can be parameterized. So this is indeed a dynamical system that is in here because it changes its state in time, but it's a non-autonomous system because there is an external input. And then there is a readout function from the state, from the dynamical system to give you the output, right? Remember that these states code the entire history of symbols, as we learned about the information processing states, right? Now, because we have only a finite number of inputs, you can say that we have actually, for example, if you have 2 inputs or 3, as here, 1, 2, 3, then we really have only 3 different types of mappings that are here, depending on your input, whether this input is 1, 2, or 3. Nothing else can happen. So it's sometimes easier to represent these mappings as Fi, and I is a particular symbol in the alphabet. But we already have an uncountable number of states. Now, in this situation, for those of you who studied computer science or you sort of are computer science minded, I can mention that with this system, you can, if you allow uncountable number of states, which is also already happening with n-dimensional interval over the real line, what can happen is that you can have even super Turing capabilities. So if you study these models from the point of view of computer science and computational capabilities, they are super Turing capabilities. But you need infinite precision in computations. And these are few names that are associated with those results. Of course, the interesting thing is that if you allow any small, even bounded noise, then you go from super Turing through Turing down, through context-free, and you end up with simply regular languages, right? So this is just for computer science sort of minded people comment, right? Now, the other important thing is that when I read my stuff from my state, so there is a readout function. So if I somehow capture the evolution of my dynamical system, when I read the outputs, this usually is a very simple function. It's either linear or it's nonlinear, but it's not very nonlinear, meaning that this is a smooth, very nicely behaved function, meaning that if you want to have two similar outputs, you need to have two similar states because you have this continuity, right? You have this continuous function. So this is very important to remember, because one good criterion of trying to understand what your state space model is doing when you look inside the states is to say, well, things that are in the state space close together, they will lead to similar outputs. That means that they code things that lead to the same continuations or the same class of the time series. So this is sometimes not very well remembered, but this is a lesson from the history where people have been doing this a lot. Now, I would like to show you that if we buy this idea of having an uncountable number of states, so we have real vectors for states, I can set up a system that looks like this. It's an affine system. It's really trivial, because what it does is that your next state at time t is just 1/2 times your previous state. So you contract your previous state by 1/2 plus 1/2 an input vector. But the input vector is because we still have discrete alphabet, so I can code my symbols of the alphabet as binary vectors, and my dimensionality just needs to be log 2 on the basis 2 of the number of symbols in my alphabet. So it's vertices of the hypercube, basically. And basically what happens is that your next state is just basically moving halfway through from your current state at xt minus 1, you move to the particular vertex of the hypercube, which corresponds to your particular input. You will see an example very soon. Halfway, and this is simply a mathematical expression of that you stay in this state and you move halfway towards this vertex, right? Initial state is in the middle. There should be 1/2 to the power of t here. Okay. Now, this is graphical interpretation of this. So now I have a state space system that is set up like this. So what it is doing, this black thing, this black area means I can be anywhere here, absolutely anywhere. And I see symbol 1. What does it mean? Now you look, I have 1 at this corner of my square, 2 at this corner, 3 at this corner, and 4 at this corner. I have 4 symbols. I need log 2 of 4, which is 2. I need only 2-dimensional square here, and I move 1, 2, 3, 4. So I contract, I see symbol 1, I move here. Next, I see symbol 4. So what I have, I already contract, it is here, and I move towards halfway towards 4, which is exactly here. So I shift everything towards 4. My next symbol is symbol 2. I contract this, put it here, but now I need to put it towards a vertex number 2. Now, what did you notice? Now, notice that this red thing in here was already the whole square in here. So wherever I was in here, meaning whatever was my previous history of symbols, I don't care. Whatever I have seen, I must have ended up somewhere in here. Whatever it was, after seeing 1, 4, 2, I can only be in this little red square in here. Because this little red square completely contains all the information about the last 3 symbols. So what do I see? The longer the common suffix of the sequences, the smaller the area. It's squeezed. For example, here I can see that all sequences that end up with 1, 4 end up in here. If you add 2, 1, 4, 2, you end up in here. So remember what I told you, that the usual thinking about state space models is that when you want to construct your outputs, usually the states that are close together in the state space lead to the same output. So if you believe in this idea, then this coding is exactly Markovian coding, right? Because it collapses sequences together based on how long is their common suffix. If I continued, and if you had a sequence that, for example, contains ends with 1, 1, 4, 2, it would be even smaller. What I wanted to say is that I get Markovian coding of the states with this trivial system that is in here. And now if I start to cluster the states, I do something even much more complicated than that. Because if you observe lots of sequences that tended to have the same common suffix, they will form a very dense cluster in here. If you see an empty spot here, that means there was never a sequence that contained any 3, right? And so on. So if you simply employed very simple grouping together of the states in terms of some clustering, then you already can obtain not Markov model, but variable memory length Markov model, which is a prediction suffix tree, which is absolutely remarkable if you think that there was a huge community of people who were just thinking about how to construct these models on the symbolic time series. And what I'm claiming here is that you simply set up a trivial dynamics like this, and you simply employ the trivial clustering, and you can extract variable memory length Markov model, right? And we will use this fact in the future. So this is what I wanted to say. You simply detect the clusters, and on top of each cluster in the dynamical system, on top of each cluster, you simply count, you simply evaluate the symbol probabilities, the next symbol probabilities, given that you were in this particular cluster. So how often it happened that you were in this particular cluster, the next symbol was A, or the next symbol was B, whatever. And this is the same in here. So it's trivial counting. And with this trivial model, you construct something that is equivalent to these guys, right? To me, this is completely remarkable. And this is a big lesson, right? So in order to show you how it works, is that consider, for example, a chaotic laser. It's a laser that oscillates with increasing oscillations. Of course, in the large scale, there are some smaller scale structures, but from time to time, unexpectedly, it collapses. So it's a chaotic laser. You can cluster it into, say, 4 symbols. This is 0. This is activity differences. This is a small increase in activity. This is a large increase in activity. Small decrease in activity. 4 means large decrease in activity. And now I want to use my trivial system that is in here, this trivial system, to predict the next state of chaotic laser. And this is it. So here is my fractal. Here are this is what happens if I run my state space model through 8,000 symbols corresponding to activity differences in the chaotic laser. And these are all simple state activations that I have seen. So note how many white spots are here. So it's a highly structured dynamical system. Not everything is possible. And these are very dense areas here that correspond to all sequences that share a very long suffix. And if I want to build a prediction suffix tree, I do a simple stupid clustering, which is in here. Just do a clustering with certain number of contexts. If I build a prediction suffix tree in the traditional way, and then take the tree and then represent the leaves of the tree. So those are the varying length Markov context and represent them graphically in the same way as the sequence, I can see that I roughly try to do the same thing. I try to cover this structure using these contexts. However, it is much more awkward. And this is much more computationally demanding than this, because this is just a trivial affine dynamics followed by trivial clustering. Now, Markov model is completely stupid because it's not smart. It just puts a prediction context, irrespective of whether you have seen that context or not, to for all symbols, for example, for all histories of up to length 4. So this is a big difference, and now you can graphically understand why systems like these are smart. And here are results on the laser in terms of negative log likelihood. So you can see that the less the better. So this is out of sample. And this is a classical Markov model. As you can still see that it has lots of prediction context. So this is a complexity of the model. How many predictive probabilities, conditional probabilities you need to build. And now you can see that it cannot do very well because it's blind. It's just constructing a prediction context for all subsequences, even though you have never seen them. And these are these continuous time simple state space models that I was describing. And this is how the traditional prediction suffix tree behaves. Those are the traditional universal information sources. You can see that it's exactly the same profile of negative log likelihood, but this is much more trivial. I have a better example of this, and this is the example of Bible, and I used it because this has been used by people who introduced this variable memory length Markov model. And what they did is that they trained a predictive model based on symbols from Old Testament books, excluding Genesis, so minus Genesis. And then the test set was Genesis, and they calculated the negative log likelihood. And you can see that this is a classical Markov model. It doesn't do very well, but then you can see all these lines are corresponding to prediction suffix trees or this continuous state space model that I introduced to you before. Now, the only difference is that the prediction suffix tree models I was training for 2 months, and these I was training for 2 days. So because, of course, it's a longer story. So here is the continuation, because now what I would like to say is that another idea that you can have is, well, I really would like to learn this dynamical system. So far, you did everything by hand. Well, you can try to do it, and this is the simplest possible example that you can know, and it's called recurrent neural network, simple recurrent neural network. And the idea is that this part I'm going to represent as neural network, and the readout part I'm going to represent as neural network. So the readout part is here, and this part is this neural network. So this is the simplest possible thing. And these are the equations for the neural network. All I wanted to say is that, again, if you look here, state at time t is a function of your input and previous state. But this is a neural network formulation. So these are activations of the neurons are the state, they are hidden neurons. This is your input. So it's a typical neural network formulation. And the readout mapping is, again, typical neural network formulation. And again, to understand what is going on in terms of symbols, let's just imagine that we have only 2 symbols, and we have our old nice task of whether it's a grammatical string or not grammatical string, right? So now I have 2 mappings. I have mapping F1, if you remember, and this is the dynamical system if my input is 1, and I have F2, which is the dynamical system if my input is F2. And for example, I start here. This is called initial state, and when I say 2, 2, 1, I end up here. If I say 1, 2, 1, 2, 2, I end up here. And I say it's grammatical. Now, in terms of dynamical system, this is our old friend here that we have seen before. What I'm really talking about is that when I see symbol 1, I need to stay here. I need to stay here. In terms of dynamical systems, what I'm saying is that I need an attractive set here. That means imagine it like you are on a mountain, you are in the mountains, and you walk on the ridge of the mountains, and this is a valley that is on the left, this is a valley that is on the right. And you have a ball, you throw the ball here and it ends up in this valley or in this valley. This is so-called saddle point because you walk on the ridge. But it doesn't matter. For symbol 1, you can see that if you are here, this is called basin of attraction, you either go and convert to this attractive set, which is a point in this case, or if you are here with symbol 1, you want to converge to here because you want to stay. You want to stay if you are on symbol 1. If you are on symbol 2, you want to jump between the two. This is called periodic orbit of period 2, and it's attractive. Why I'm saying this? Because if I want to train it, if I set it up as my neural network, and it can be an even more complex neural network, I need to train these weights. What happens? Well, I know that I need to create attractive sets, right? Here, or even attractive periodic orbit. But let's think about these attractive sets. I need to shape my attractive sets. But if you are in the neighborhood of attractive set, the derivative of the dynamical system is very small because nothing changes, right? If you are very close to stationary point, nothing changes. That means there is no difference in your previous and current state. That means the derivative is close to 0. But if you think about backpropagation, you need to backpropagate the error signal in time, right? So if I observe lots of 1s, I may easily forget whether I was in this state or in this state because I cannot propagate this information. So we have in a catch-22, we are in a catch-22 situation. In order to learn a structure like this, I need to set up the parameters of my network so that I create attractive sets because I need to remember events. As soon as I start to create attractive sets, I propagate my gradient information through chain rule, and I need to propagate them in the neighborhood of attractive sets. That means I multiply with lots of small numbers because that's like a chain rule of derivatives, right? So my gradient information diminishes, it vanishes. So it's called vanishing information latching problem, vanishing gradient problem. And surprisingly enough, people in the deep network community also came up with this problem because they have deep networks, and deep networks are almost the same thing as recurrent networks that are unfolded in time, you know. So if you want to propagate the information through a lot of time steps, that's basically you have a deep network. That's what happens. And this is the basic problem why it is so difficult to train these networks. And this is why we have another idea. We call it also a curse of long time spans. And we deal with this in two ways. It's not trivial to train recurrent networks beyond finite memory. So we either say, when we have a fading memory assumption, so we say, you know, we don't really need to remember that much from the past, then we are okay with having systems that are based on something like contractive behavior. Those are reservoir type of models. And those are all kinds of models that the basic idea is this, what I just showed you. You don't even train, you just set it up so that you have a smart coding of the states that is Markovian, and you sort of remember the future, remember the past up to the bit that it's like a fading memory, right? The longer you go into the past, the worse it takes. Or you have LSTM and gate units, and those are the architectures that try to deal with the problem of propagating the gradient information around attractive sets. And it's a hack. It's an engineering trick that instead of classical neurons, they have so-called gating units. It's like a big unit where you are allowed to propagate information, even though normally the Jacobian would be very close to 0, right? So it's a smart trick. So those are all these kinds of gate units architectures that you have starting from LSTM. The reservoir computation models you may have encountered, echo-state networks, liquid state machines, or fractal prediction machines. Fractal prediction machines are exactly the systems that I showed you before, right? So unfortunately, I can see that my time has elapsed, basically. So I had more mathematical arguments to show you why this is so, what I was saying. But I think, let me just show you what I would just mention one more thing, right? So there is also theoretical grounding for all these things, right? So, for example, we can show that I set it up in a smart way, you know, this type of dynamics, but you can show that any simple recurrent neural network that is initialized as usual, meaning with small weights and blah, 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 has this property of Markovian coding, and we called it Markovian architectural bias of recurrent neural networks. Shocking result, even without any training, recurrent neural networks already have the power of the most universal information source that we know about, prediction suffix trees. This is pretty shocking, but it is the case. You can prove it. There's a theorem. And there is another thing that I would like to tell you, and I will just finish here. I had prepared lots of other stuff, but there is a very deep correspondence between the complexity of how your state space is looking, and we can. It's basically a geometrical measure of complexity. It's called fractal dimension. And the complexity of your input that you feed into your network. And again, there are several measures, but there is information theoretic measure that we call topological entropy. And you can show that up to scaling that are exactly equal in those types of architecture, which is again, a really shocking and surprising result, but it is the same. So meaning that the state space organization is actually coding your input history in a very meaningful way. And I had some nice illustrations with hidden Markov models, but I would probably finish here. And what I would like to say is this: few take-home messages, right? The first take-home message is state space models represent a huge class of systems that you would normally even think about as the same, starting from computer science models such as finite state machines, Mealy machines, and so on, going through probabilistic stochastic machines, going through Kalman filters, extended Kalman filters, recurrent neural networks, LSTMs, reservoir models, autoregressive models, and so on. All these kinds of models are state space models. What do they have in common? If you want to change their parameters, if you want to fit them to your particular data, it is difficult to do. If you want to remember information from the past that is long enough, that happened some time ago, if you want to remember it, that's difficult to learn, very difficult to learn. And I try to illustrate it why this is so using these attractive sets and so on. We need to do tricks in order to do it. And that's why we have LSTM architectures. That's why we have gating units. Another thing is you don't have to do it if you're okay with fading memory. They can be very long, but if you're okay with fading memory, you can have completely arbitrary, even random architectures that have this contractive property, and they are going to work. But why they are going to work? Because they are all Markovian. That's the main take-home message, right? And unfortunately, I didn't have time for more, but thank you for your attention.
Thank you, Peter. I feel we need more another session to go through the rest of your talks. Certainly, I think I know some people may have another meeting scheduled next hour. So, sorry to cut it short, but certainly I will see if in the future we'll have another occasion to get you back to finish off and more advanced. So, open to questions.
Wow, this is the most advanced audience. So either like I confuse them all, or
certainly I was intrigued by your kind of comparison between macro models and the kind of state tree models. Certainly, in my opinion, Markov models is just purely looking at one level, just probabilistic dependencies, isn't it? Without looking at attractors, kind of hidden states. So it's some slides you couldn't get onto it is the hidden Markov models.
Right. Yeah.
Does hidden Markov model do better?
So I would like to argue that the problems that you have with hidden Markov models, why we need to work so hard for the hidden Markov models, is, we had to develop forward-backward algorithms and stuff like this, is that we have unobservable states.
Yeah. And
the problem with unobservable states are basically the same kinds of problems that you have seen in recurrent neural networks. When you wanted to, then you have unobservable states, so you need to create some idea of the state space. So in case of hidden Markov models, the situation is slightly different because the states are set, right? It's very clear what it is, but it's very difficult to know in what state you were. And the situation becomes even harder if you observe very long time series, because then the possible number of possible state paths you could go through grows exponentially. So, so you can't really, and this problem simply cannot be eliminated in any reasonable way. And that's the problem of unobservable states.
Can't we just use massive amount of data to train? It's similar to the autoencoder kind of ideas. So you kind of experimentally and then find out the usefulness of states, hidden states.
Right. No. So one thing that you need to understand is that no huge amount of data is going to help you to deal with a problem if you don't know how to organize your states, your state space, how to do it, because nobody is going to tell you. You have to figure it out for yourself. It's very different from learning input-output mapping, where you say, this is your input, this is what you need to produce. This is your input, this is what you need to produce. In terms of state space models, you have to figure out what are the dynamical systems. You have to train, you have to change the weights, that you change the dynamics. And nobody is going to tell you what this dynamics is. In terms of hidden Markov models, at least I tell you how many states you have, but that's all. You need to figure out for yourself what are the transition probabilities. Nobody is going to tell you anything, right? And this is the problem. This is a big problem with unobservable states.
Yeah, I just also wondering whether this model can be applied to kind of a common kind of language modeling problems. For example, hidden Markov models being widely used in speech recognition, speech comprehension, whether this kind of state space models can be applied. So in the sense, can make some improvement on that. At the moment, it's mostly kind of dominated by the hidden Markov models.
So hidden Markov models, but note what they did. They constructed these chain hidden Markov models for speech recognition, and that helps a lot, because I say that I brutally simplify the state transition. It's no longer any state can change into any state. No, you can only go in a series, and the only problem is the duration. How long are you going to stay here? Then you move to this state. How long are you going to stay here, and so on? And you don't know when you are moving. And these states represent sounds, and so the emissions from these states are corresponding to sounds. And sometimes it's very difficult to know exactly when you go from one sound to another, because you have continuous speech signal. But the way they dealt with this problem of hidden state space, unobservable states, is that they say it's unobservable, but I have very strict constrained state space transition structure. That is much more simple.
Yeah, otherwise it would be difficult to work out, isn't it? So very difficult. I just wondering, any people in the audience are working on the language-based or sequence-based problems, whether they have any thoughts on the state space models?
So they probably would use LSTM or other types of networks now, but the problem with that is that you can chunk through whole books and whole proceedings through LSTM, and it will do something, but you have absolutely no clue what is going on, which is worrying for me, right? You know, so one thing is engineering application where you say the only claim to glory is that it works. But I think we should gradually move away from that. Right. I can see two questions here. How do we relate the new technologies of transformers and attention mechanism regardless of design? So that's a very good question. And so my answer is the attention mechanisms, right? So what was the problem? So if you, for example, remember what I said, you have an event here, and then for 100 time steps, nothing important happens. But all of a sudden, for my current time, if only I could remember what happened 100 time steps back, it would really help me to do my next action, for example, in a robot or make next prediction. But it's very difficult. So these attention mechanisms and gating units, what they do is that they try to say, don't try to pay the same amount of attention to everything that happened in the past, because it's not of the same relevance for your task. And those are indeed, this is also purpose of these gating units and attention mechanism, but that's a good question. How do these relate when dealing with multivariate time series? For example, when models take into account a large number of variables changing over time. So I would say that multivariate time series makes things more difficult, right? So not only you have univariate time series, but now you can have potential dependencies across space. So you really are building a spatial temporal model, and these dependencies can change over time. So what people do is that they try to either reduce the dimensionality and then apply a state space model, or you would need to build a dedicated state space model that also tries to take into account the dependencies across space, right? So if I, for example, had some covariance function or something that I try to learn in my multivariate input together with the state space, then I can learn a smart low dimensional projection of my inputs to the state space. Yeah, but it complicates things.
I think I'm not sure whether we have further questions. Otherwise, I think let's thank Peter again for his a wonderful talk, and that's certainly
thank you, guys.
Be beneficial. Right, thank you.
Thank you.
Thanks, Peter.
Thanks. Yeah. Thank you. See you, guys. Thank you.
Right.
I hope it was useful. Yeah. Thanks.